Hello, welcome back. In this segment, I will prove this theorem that if the decisional Diffie-Hellman problem is assumed to be hard, then the Diffie-Hellman key exchange algorithm is secure. In order to prove that Diffie-Hellman key exchange is secure, it's enough if I prove that the probability that the key exchange experiment result in 1 is negligible. So I request you to watch the previous segment where I defined this key exchange experiment more formally. I'm using the same notation. There's one small modification I need to call out here. In the previous segment, when we defined the experiment, we said that the adversary may either get the actual key or a random number. And the random number I mentioned there was an n-bit random number. Okay, but if you remember how Diffie-Hellman key exchange works, you get a common key. Both Alice and Bob get a common key, but that key is actually a group element. Okay, if we are working with a cyclic group, the shared secret is a cyclic group. So in this context, in this theorem, I'm going to make assumption that either a random group element is given or the actual element that both Alice and Bob arrive at the final stage is given to the adversary for this experiment. Okay, that's the important clarification. All right, so in order to prove DH key exchange is secure, we need to prove that the probability the key exchange experiment results in 1 is negligible, meaning the adversary cannot distinguish between a group element, a randomly chosen group element, versus the shared secret that both Alice and Bob have, which is also a group element, of course. Okay, remember how the experiment goes. First, we randomly select a B, right? B can be either 0 or 1. That means with equal probability, right? B can be 0 with the probability of half. B can be 1 with the probability of half. Okay, let's assume B equal to 0. In that case, we need to check whether the experiment results in 1. Okay, that's first part. The next part is if B is 1, we need to check what is the probability that the experiment is ending up with 1. Okay, why am I multiplying with half? Because B itself is uniformly chosen, right? So with the probability of half, B can be 0. With the probability of half, B can be 1. All right. Now let's dive into the details of the next step. Given that B equal to 0, what is the probability that the key exchange algorithm, probability of key exchange algorithm being 1, key exchange experiment rather, results in 1? That means the subroutine adversary, polynomial time adversary, must give us 0. Since we are giving 0, if he was able to predict that indeed the input was g power xy, adversary is saying 0. Okay, that's the reason why I say key exchange result in 1 means the adversary must also output 0. All right. Similarly, if B is 1, the adversary must be able to say, okay, well, the third argument, the g power x, g power y, g power z must be a random element. That's the reason I am putting adversary saying 1. Okay. Because we want the key experiment to succeed here. That means the adversary was able to successfully say, yeah, you gave me a random element. Okay. Now I'm just doing some very basic probability adjustment, right? Probability of adversary outputting 0 is same as 1 minus probability of adversary outputting 1. And then I just reorganize some of the common terms. Like I took the half outside, and then I put the positive term first and then the negative term next, and I plugged in an absolute value. Okay, that means we know. But this problem is something that we already saw, that this is nothing but decisional Diffie-Hellman problem. Okay, and we know that is hard. That's the assumption that we are given. If that is hard, that means this probability must be negligible in the parameter of n. N is the security parameter. That means we arrived at a very interesting result that the probability the key exchange experiment output 1 is bounded by a negligible value. This is negligible and plus half. Okay, so it's basically bounded by half plus some negligible function in n. Okay, then we can conclude that the decisional, then we can conclude that the Diffie-Hellman key exchange algorithm is secure. Okay, so if this is a bit confusing, I request you to watch the previous segment first, because I defined the experiment more formally there with all the notations. Here, this is just a proof based on the notations we discussed in the previous segment. Okay, G is a cyclic group. G is small g is the generator. and small q is the order of the group, the cyclic group order. And g power x, g power y, g power xy are all terms that we have been using for quite some time. All right, that's all. Thank you very much for your attention.